And luckily my drawing pad works, so we can have a look at this task 35 about filters. And so we have a quite simple circuit. We have some resistance and some resistor and some capacitor. If we just look at the two, and if this output is really open, what type of connection is this? It's just a simple series connection, even if it does not look that like a series connection, but it is in series. And it's also written here. They are in series. Okay. And so we apply some sinusoidal voltage at the input, and then we measure the output voltage. And if this is a linear resistor, and if this is a linear capacitor, then the output voltage will also be sinusoidal. It might have a different amplitude, of course. It might have a different phase angle, but in general, it will be also a sinusoidal output voltage, just with a different frequency. With the same frequency, different amplitude, different phase. And so what we should calculate is, using the voltage divider rule, this ratio between output voltage and input voltage, and then calculate this for different frequencies. And we can maybe decide and discuss what function does this circuit fulfill and what kind of filter is this. So if we start with task A, and if I try to write this, what is the output voltage V2 as a complex phasor with respect to the input voltage V1 as a complex phasor? And how can we calculate this ratio of the output voltage is the partial voltage, the input voltage is the total voltage across this voltage divider. How can we calculate this voltage divider? How did the voltage divider rule work? If I go to a new page and just write or draw two resistors, so we have one resistor. I will use the German or European symbols. And a second resistor, so this is resistor R1, this is resistor R2. We have total voltage drop across both resistors, and we are interested in this voltage V2. So how can we calculate this voltage V2? So it's total voltage, exactly, multiplied with the partial resistance, the resistance where we have the voltage drop across, and then divided by the total resistance. And so we could also bring this V to the other side, and then we would have partial voltage divided by total voltage is partial resistance divided by total resistance. Okay. So now how to apply this to this circuit here? What is our partial resistance? Yeah, so this is the resistance, the complex resistance of this capacitor. And how do we call complex resistance? Yeah. So if we maybe go back to the second page here, or maybe if we go even to maybe a third page and do a quick reminder and a quick summary of what are the basic elements that we have. We have resistors, we have capacitors, and we have inductors. And so what rules do apply for resistor if we have a resistor and if we have, so this is the symbol, and if we have a current going through the resistor and a voltage drop across the resistor. So, what rule applies? Yeah, so we can write down Ohm's law in a way that we say voltage across the resistor is resistance times current. Or we could also write it in a different way and say the current through the resistor is the same as the voltage across the resistor divided by the resistance. And this will work for DC current and voltage, and this will also work for AC current and voltage, will work for any time function of current and voltage. So if we have a capacitor, as in our exercise task here, and if we have a current going through the capacitor, I will call this IC of t, and the voltage drop is Vc as a function of time. So here we could also add this. This is both as a function of time. So how does voltage and current depend on each other on a capacitor or at the capacitor?
Well, I guess charge divided by current. So.
Yeah, so I could say this is the charge as a function of time divided by the capacitance. Or is it divided by the capacitance? Let me think about this for a second. Voltage, capacitance is, charge divided by voltage. So this makes sense. And so, now we have charge. How does charge and current belong to each other? But current times time only works, I think, if we have a constant, if we have a DC current. So in the more general case, Q of t is not current times time, it's current integrated over time. And if we take like the opposite of this formula, then how can we get the current? So this, of course, here the current also depends on time. So how can we get current from charge? It's a derivative, exactly. So if the charge changes over time, then we get a current. And so now if we say, okay, our charge here is voltage times capacitance, then we get that the voltage the voltage through the capacitor is capacitance times the time derivative of the voltage drop across the capacitor. And so, I mean, here it's just voltage divided by resistance. Here it's current is time derivative of the voltage times the capacitance. And we can also, of course, go back to like this equation here and say the voltage drop across the capacitor, maybe I can just add this here, would be 1 over C and then the current through the capacitor integrated over time. And so we don't use this element in our exercise task, but if we just for completeness add here the inductance, and so we have some current IL going through the inductor, and some voltage drop across this inductor, R, C, and L. So how do current and voltage on the inductor depend on each other? Or what is the relation between them? Well, remember what we discussed, that C and L are kind of dual elements. And if we just change C by L and voltage by current, then we get the very same equations. Yeah, so here we get a voltage across the inductor if the current changes over time. So if the voltage changes, we have a current. Here, if the current changes, we get a voltage. And the other way around, we get a current, or we could also calculate the current by doing 1 over L and then integrate the voltage drop over time. And so the dual element for the resistance would be some conductance, but conductance at the end is also, just like a resistor. But we could also say we have a current going through the conductor and we have a voltage drop across this conductor, Vg of t. So this is G, and then it's the same with C and L, that here we can also say, okay, the current going through this is 1 over G times the voltage, or that the voltage, the voltage is 1 over G times the current, and the current is G times the voltage. Okay, so these are our functions in general in time domain. And remember, the problem is we could do all this stuff in time domain with this time derivative and time integrals here. But the problem is, if we would now try to go back to our circuit, we could not write a simple rule like this. We could calculate this voltage here from the current, for example, but then, as you've seen, so the voltage drop is time integral over the current, or we could calculate the current if we would already know the voltage is the time derivative of the voltage at this capacitor, but this would lead us to differential equations, and we don't want to solve differential equations. So what trick did we do to transform these time domain equations into frequency domain equations? And then you mentioned something that we write down some x here, or I would rather use some z, or some z, some impedance in this case. So how to go from time domain into frequency domain. How to write the same stuff but with complex phasors. And the simplest thing is maybe if we start for the resistor. So now if I say for the resistor, I don't have a time function here anymore, but now I have some complex phasor that stands for some sinusoidal changing voltage. So I have voltage phasor and I have a current phasor. Both are complex. That's why they get this underscore. How does the equation look like? Same as before. Yeah. Okay. And so here we could also say IR is VR complex phasor divided by R. Okay. For the resistor, nothing changes. Ohm's law in time domain is the same as Ohm's law in frequency domain. Okay, then probably more interesting is if we look at the capacitor and at the inductor. And so how does, for example, if we start with this equation here, how does this equation transform into frequency domain? If we have a time derivative of something, what does the time derivative change into? And so if you remember, we said that our sinusoidal voltage, yeah. So for example, your sinusoidal input voltage, sinusoidal output voltage. No. V of t was something like we had some amplitude and then we said, okay, we need to have some sinusoidal function. This depends on omega times t and phi. So this is the amplitude. This is what scaled our time domain function in this direction. How was this called? Angular frequency and the angle or the phase angle, some phase shift, something like this. And so, yeah, we could write this also as the, in this case, the imaginary part of the same amplitude multiplied with some exponential function that has the same argument. Remember, because e to j alpha or e to j phi is the same as cosine phi plus j sinus of phi. And so this is really mathematically the same. This just looks a little different than our plane sine function that we had before. But yeah, here it's somehow already getting complex, and now I could write, it would be the same as the, or maybe I write it below, then I have more space on the other side. I could also write it's the same as the imaginary part of V times e to j phi multiplied with e to j omega t. So I just split up this exponential function, and now these two together here, this would be our complex phasor. And so this is what our complex phasors here on the next page really mean. And so if you would insert the equation that we set up here, if you would insert this equation into Ohm's law, nothing really changes, and that's why we can just write down the very same equation with phasors. But now we have here some time derivative. And so if we would now calculate the time derivative of our voltage function here, So what happens? So it's time derivative of whatever is written here. So the imaginary part of this amplitude multiplied with ej phi and this exponential function. And so what can we do with this time derivative? Or what can we do in this mathematical formula?
I got the first boss, like the amplitude and say.
Exactly. These are constants. They don't depend on time. So we can just move them in front of this time derivative. And we can, without showing a mathematical proof, but we can interchange the order of if you calculate the imaginary part at first of something and then calculate the derivative, or if you calculate the derivative first and then the imaginary part does not change anything. So we could interchange this order. And so then what is left? So let me write it like this, that we have the imaginary part of v times, or the amplitude in vj phi. And now we have the time derivative of our complex exponential function. That is what is left. And so what is the time derivative of this complex exponential function? What is the derivative of some exponential function? Itself, it's the exponential function itself, but it's not e to t, e to the power of t, it's e to j omega t. So we multiply by j and omega. And that's the important thing. We multiply by j omega. So at the end we get, it's the imaginary part of v times e to j phi times e to j omega t and multiplied with j omega. And so if we compare this, we have amplitude, we still have this phase angle, we have the dependence on j omega t, but what was added is the j omega. So this means what is a time derivative in time domain, in frequency domain, it's a multiplication with j omega. That's the important message. And so we could repeat this also for the time integral. So what happens if we take this sinusoidal voltage function and if we integrate over time? And so, then we would write this integral. I will write ... So, finally, we would have the time integral over this exponential function integrated over time. So what is the time integral, or what is the fundamental function, the antiderivative of the exponential function? This program is also really annoying. What is the antiderivative of the exponential function? It's exactly, it's the exponential function once again, and then, and then divided by j omega. So what we end up here is also the imaginary part of amplitude multiplied with complex phase function there, multiplied with ej omega t, and then we divide by this inner derivative of the exponential function. So time derivative means multiplication with j omega, time integral means division by j omega. So if we go back here So now I see complex phasor, and here we have the time derivative of this complex phasor, and time derivative means multiplication with j omega. So we get j omega c times our voltage function. And so if we formulate this the other way around, with the voltage at the beginning, then we would get it's 1 over j omega c multiplied with the current through this capacitor. Have you seen this equation before? I think we've, yeah, or this one. I think we've discussed it last time, but okay. Yeah, so for the inductor, if we say the voltage drop across this inductor is a complex phasor, and here we have time derivative of the current. Time derivative was multiplication with j omega, so we get j omega L multiplied with VL, no, with IL, with the current. This is somehow hidden behind my camera window, so maybe I will switch off my camera for a second. Okay, and the current then, if we just take this equation and rearrange this for the current, then the current through the inductor would be 1 over j omega L multiplied with the voltage VL. And so now we see, at least I see, the beauty of this, because what we did here in time domain was somehow straightforward, and this is what we knew before, that if charge changes over time, then we get a current, and if voltage changes over time at the capacitor, we get a current, or if the current changes over time at the inductor, then some voltage is induced. But this is all time domain, so we have this ugly, nasty time derivative, we have time integrals. And so if we go into the frequency domain, now we need to calculate with complex phasors. This is the disadvantage, but we get very similar algebraic equations as before. And if it's some resistor, if it's some capacitor, if it's some inductor, we always get similar stuff like voltage is resistance times current. Voltage is something times current. Voltage is something times current. And so how do we call this? And how do we call this here also? This quantity has a name. This is impedance, exactly. So this is what we call ZZ. And so then we could also just simply write it's ZZ times the current. And this is what we call ZL, impedance of the inductor, and then we could just write ZL times the current. And I mean, here we could also say, okay, this is the same as ZR, and we could write ZR times current. Yeah, no one really does this, but sometimes I also do it. Okay, so this is what we call impedance. And so now if we go to the other side here and say, if we would have this IG current through some conductance, maybe some conductor, and it's G times the voltage drop across this conductor. this equation in time domain, this equation in frequency domain, they would be also the very same equations. So we can see now here and here and here, we also have the same stuff. We have current is something times voltage. Current is something times voltage. Current is something times the voltage. So how do we call this factor or this factor? This is admittance, exactly. And so this is what we would call Y, Z in this case. So I could also just write it's YZ times the voltage, or YL, the admittance of the inductor. And then this equation would be YL times VL. And so we get very simple equations once again for this. And so using this, of course, we could also simply rewrite our voltage divider rule here. Just that in our initial voltage divider that we have here, that there's a resistance, and not the second resistance, but the capacitor. But still we can write the very same formula as the one for resistances. But instead of resistance, right, we just use impedance. And so as discussed and as mentioned before, partial voltage, partial impedance, total voltage, total impedance. So the partial impedance is the impedance of the capacitor, and the total impedance is the impedance of the resistor plus the impedance of the capacitor. Very simple. So next step, what do we do? We insert, what is ZZ? What is ZR? How do they depend on angular frequency? So maybe I have some space here left on this side. So impedance ZZ is 1 over j omega c. ZR is just R, and ZZ is once again 1 over j omega c. Okay, now we get, this fraction, double fraction, probably not that nice. How can we simplify or rearrange this to make it look a little better? Yeah, we can expand this equation by j omega c. So we multiply the numerator by j omega c, and then we get just 1. And if we multiply the denominator by j omega c, so if we multiply this with j omega c, we also get just a 1. And if we multiply this with j omega c, then we get 1 j omega r c. And this is now some kind of nice equation to deal with, because it just contains the value of the resistance, the value of the capacitance, and our angular frequency. Okay. I would say task A is finished. Questions so far? Okay. So now we can probably continue with task B. What is the value that we get for this for certain frequencies? And yeah, how would you do this? How would you solve this? Just insert the values. And of course, I'm always a bit lazy and I don't have a calculator with me. And so it's also strange values here that are probably difficult to calculate by head. So what we usually do is we use Octave. Unfortunately, my mouse is still not working. So let's try to make this a little smaller and try to fit this here somewhere on the screen. So at first we probably need the value of the resistance, which is 10 ohm. And then we need the value of the capacitance, which is 318.3. And micro is 10 to the power of minus 6. So E minus 6. And so then we have 3 frequencies given, and I will directly write them as some vector, some array. So we have 5 Hertz, 50 Hertz, and 500 Hertz. And so then the next step probably is we need to have omega, our angular frequency. So how can we get angular frequency? 2pf. Omega is 2 times P times F. And so then we get these angular frequencies. And yeah, as we just discussed at the beginning, happy 2025. So interestingly, if you take e to the power of p, and if you take p to the power of e, and if you take the seal of this, so yes, it means just round to the nearest integer which is below this, and then square it. Oh, no. Well, not seal. I was wrong function. Floor. Nearest integer below. Then we have 2025. Okay, so this is what works with P and E to get 2025. So going back to our task. So now we can just go back and set this into our voltage function here. So V2 to V1, I will call it in this strange way, is 1 divided by 1 plus J. And remember, it was maybe more secure to write 1J times omega times R times C. And if I hit enter, I expect that MATLAB throws some error message. But yeah, let's try. Yeah, as said, does not work, or Octave throws some error message. So why does it not work in this case? If I show the full message, it says non-conformant arguments. Our operator, I'm not sure if this means operator, but yeah, whatever we input there at first is 1 by 1 and the second is 1 by 3, and that's why it does not work. So what does this error message is trying to tell us?
Instead of 1 divided, you have to like auto.
Yeah, so this means here we have some scalar number. We have just 1, and our omega was 3 values. And we cannot divide a vector or a scalar of 1 by a vector of 3 elements. And we don't want to do this. We don't really want to divide by a vector. Also, there is no vector division. We want to do this element-wise. And element-wise works with a dot. So if we take a dot division, then it works. Now we get 3 results. And of course, because there's something complex in here, now we also get a complex ratio between these two voltages. And these complex numbers are output as real part and imaginary part, which is probably not super helpful in this case. And that's why, what does the task suggests here? To display or to calculate this voltage transfer ratio not as magnitude and phase, what Octave just has done, but not as real and imaginary part, but as magnitude and phase. So how can we get, so now we have this, we have our three values here for this voltage transfer ratio inside this variable. How can I get the magnitude of this? It's this, okay, so the real part I get with real, and then I can square it, and then I can take the imaginary part, this is what I get by imaginary, and I can also square it, and so then I take the square root of this, and if I try it like this, there will be also an error message, because this squaring only works for scalar values and not really for vectors and matrices. I want to have it element-wise. And okay, so then there I get magnitude. Would there be a more simple way to get the magnitude? And if I ask like this, probably yes. What is another name for magnitude? Absolute value. And so if we just take our function here and use abs, and we get the very same result there. Okay, so the magnitude looks like that for this frequency, it's almost 1. For this frequency, it's 0.7 something. And for this frequency, it's kind of small. Okay. Now, the next thing that was suggested here is to also look at phase. So how do we get the phase of this?
The inverse function of the tangent from if your imaginary part of.
Exactly. So if we once again take the imaginary part of this and then divide by the real part of this, and then take the inverse tangent or the arcus tangent of this, and and so then interestingly we get just one value, because vector divided by vector in this case gives something like a scalar value, but we want to have 3 values, so of course we need to have this dot operation here once again. And the result will be in radians, right? So if we want to have this in degree, what we need to do, how to convert from radians into degree. What 180 degree is equal to p radians, so we need to multiply with 180 and divide by p. We want to get rid of the radians, so we divide by p. We want to have degree, so we multiply with 180. Okay, and so then we get these phase angles. There is, of course, also a more simple way to do this. So there is some angle command. And if we just use this and multiply with 180 divided by P, then we get the very same result there. So absolute value gives magnitude, or abs gives magnitude, angle gives phase. And so we can see, okay, the phase shifts or changes in a way that for the low frequency, we have no phase shift. And for this medium frequency, let's say in this case, we have something like 45 degree of phase shift, minus 45 degree of phase shift, to be more precise. And for higher frequencies, we have something almost 90 degree of phase shift between output voltage and input voltage. And yeah, so what we can easily do now in Octave here, for example, is, so instead of using just these 3 frequencies, we could use even more frequencies and say we use some logarithmically spaced frequencies between why not use this 5 and 500, and we can extend this in a second and use, 500 values. So now we have 500 frequencies, right? 500 values for the frequency, and now we can just repeat the calculation that we did before. So we can calculate our angular frequencies. Now we get also for omega 500 values. And we can recalculate our ratio here. And with the semicolon, I will omit the output. So we also have 500 values for this. And so now, for example, we could plot, maybe plot at first, plot magnitude versus frequency. And then we get something like this. And then it does not look that nice. Because it's like a 1 over omega function. So we get some, in German it's hyperbole. I don't know how to translate it into English. It's probably something similar, but just pronounce it a different way. Hyperbola. Yeah. And so it's difficult to see here. We can make this plot a little nicer and a little more understandable if we use logarithmic scaling on both axes, or if we would scale the amplitude axis in dB. Remember in the very first exercise, I think we discussed the dB scale, which was some logarithmic scale, and the advantages and disadvantages of such a logarithmic scale. And so if we do the same plot in a logarithmic scale, it looks much nicer. And we see 5 to 500, interesting. We see that for small frequencies, this ratio is about 1. And then for higher frequencies, I forgot I just wondered why my frequency range is going so much up, but because I forgot the log 10 here, and then it was using natural logarithm. So just let's do the calculation quickly again. And now if we plot it, okay. Yeah, so this is for the low frequencies, the amplitude is 1 and then there is some break somewhere. And then for higher frequencies, this amplitude is going down. So this is what happens to the magnitude. Yeah, and maybe it would be interesting to extend this frequency range and maybe already start at 0.5 and then at 5 kilohertz of frequency, start at 0.5 hertz and at 5 kilohertz. So calculate omega once again, calculate this once again, and do this log-log plot. Yeah, and then it looks like this. So low frequencies get through, high frequencies obviously get attenuated. And if I open up a second figure, and if we in the second figure plot the phase, so with respect to frequency, we take the angle of our output function and multiply this by 180 divided by p. So in the second figure, so this is magnitude and this is how the phase changes over frequency. And there you can see that the phase starts at 0 and then ends at 90 degree, and the 90 degree phase shift is the phase shift due to the capacitor, due to this time derivative. Remember what we did here. So if we start with the sine function, calculate the time derivative. Time derivative of a sine function is cosine function, and cosine function has a 90 degree phase shift against the sine function. Or J is also the same as e to j 90 degrees. So a multiplication with J is also like a 90 degree phase shift. And this is this 90 degree phase shift that we get here for high frequencies in this plot. So we can come to the last task and discuss what function does the circuit fulfill and what kind of filter is it. So this is the amplitude behavior. This is the phase behavior. What is the purpose of this circuit? It's a low pass filter, exactly. So it's a filter circuit that certain frequency components can get through and certain frequency components get attenuated. And in this case, the low frequency components, they get through, and the high frequency components, they get attenuated. And the higher the frequency, the more they get attenuated. That's exactly the function and the purpose of this circuit.